Mainly today, most probably we are using the problems concept of Picard theorem, Lioli's theorem, and properties of entire function, behaviors of entire function, like that. I'll start a very simple basic problems for part C question. I'll write, then you try to solve. From the response, then I will explain what is that meaning and how to solve, how to do it. Anyway, we start the session. The first problem is a simple problem. First problem number one, let f be a non-constant entire function, non-constant entire function, and let E be the image of f, then E is on open set
Excuse me.
B.
Sir?
Please, someone
Excuse
mic
me,
is
sir.
open. Yes, madam.
Sir, your board
Yes.
was blur for some time. Now it's okay, sir.
The board is okay.
Now okay. Yeah.
Okay. Sometimes actually the Zoom Meet camera is, it will be zoom in and zoom out. But when I am doing classes in the Google Meet, there is no zoom in, zoom out. But in the Zoom meeting, this happens. We can't able to control. So maybe that time it happens
Now
sometimes.
it's better, sir. Now it's
Okay,
better.
okay, madam. E intersection set of all Z and C such that mod Z less than 1 is empty. B. E intersection R is non-empty. And D option is bounded set. A is a bounded set. Please do the problems. Just first read the problem. Read the problem. What is given? Let f be a non-constant entire function. Given f is a non-constant entire function. Let E be a image of f. Image of f. You know what is the meaning of image of f. Then what is your conclusion about image? The image always open, and take image set intersection with the unit test is empty, and image intersection R is non-empty, and it is bounded set. What is your idea? Participant, please. So given f is a non-constant entire function. Okay. Is there any idea? No idea. Okay. I try to explain very clearly. This is a very simple problem. This is a theoretical problem. Option repeated. Where it is repeated? A is an open set and this is an empty set. Option B is an empty, but I written here B instead of I write C. Now it's okay. Okay, fine. And D is bounded. Anyway, we try to solve what is it meaning. First, write we set of all f going from C to C such that f is non-constant entire. Yes, madam. Non-constant entire. This is a V set. V set means what is the meaning of V? So any element in the V is a non-constant entire function. For example, f of z equal to a power z is a non-constant entire function. This is an element of V. What about the g equal to z identity function? For every z in Z, this is an element of V. Okay. Now the people asking question: take any element in the set. What the property of and the set V? V is a non-constant function. In C to C, we have a lot of complex valued function. From all those complex valued function, not necessarily for entire, but we are collecting non-constant entire function. So that is a collection for non-constant entire function. If you take any element, always has this property or this property or this property, this property. That is a question. Maybe infinitely many non-constant analytic functions are there. Non-constant entire functions are there. Among infinitely many of the non-constant entire function, we take any entire function from the infinitely many non-constant entire function. That element should always has this property or this property or this property or this. We have to check. Okay. You know entire means. What is the meaning of entire? A function which is analytic in the whole complex plane. That is called entire. A function is analytic in the whole complex plane. That is called entire. Perfect. What is the meaning of analytic? What is the meaning of analytic? What's the meaning of differentiability? Is there any difference between differentiability and analyticity? Yes or no? Is there any difference between differentiability and analyticity? Is there any difference? Differentiability, when we talk about, it's a pointer.
So that's a response. The image is whole complex plane or complex plane singleton element A. This is the response in the chat box.
What is the response, madam? Again, once more, please.
The image is whole complex plane or complex plane or singleton element A.
Oh, very good, very good. Somebody they said answer is when the entire function whose image is always whole C or except some point in C. Some point in sense at most omit one point. That is answer is correct. But I'm trying to explain the basically. So that GV, I don't know who is that GV. He, I don't know, but they are responding very quickly. Very good. Very good. Okay, what is the difference between analyticity and differentiability? So just I am explaining little bit, then we will do the problem. Okay, somebody's written that in the, okay. F is differentiable. Suppose this is our domain. Domain means open connected set. Is a domain. A point Z0. Limit Z goes to Z0. F of Z minus F of Z0 by Z minus Z0. This is exist and finite. Then we say that F is differentiable at this point. F is differentiable when the limit exists and finite. When the limit exists and finite, then F is called differentiable at Z0. This is a differentiable at a point. Now, what is the meaning of analytic that point? What is the meaning of analyticity that point? We need a difference. Okay, analyticity is a global property. So differentiability is a single point. It's a local property. Okay. Anyway, so F is analytic. Just I am written a single line. F is analytic. With analytic at Z0 if there exists a neighborhood of Z. There exists some neighborhood of z naught such that every point in the neighborhood is differentiable. In the sense, we have to say f is analytic at z naught if there exists some neighborhood of z naught. There is some neighborhood z naught. Every point in that neighborhood f is differentiable. Some neighborhood. Okay, at least one neighborhood you can able to find a one neighborhood around that z naught. Every point in the neighborhood is f is differentiable. Then f is called analytic at that point. Okay, like this. Suppose assume that this is some neighborhood. In this neighborhood, every point is differentiable. Then we call that f is analytic at this point. Okay, that is analytic. Now, what is the meaning of entire? Suppose now your domain D equal to C. You take any point in the complex plane, some z naught. There is some neighborhood. Every point differentiable. Then we say that f is analytic in that point. You take anywhere in the complex plane, any point in the complex plane, that point should be analytic. Analytic in the sense, you take any point, there is some neighborhood. Every point in that neighborhood, f is differentiable. Then we say that f is analytic everywhere. When we say f is analytic everywhere, we can say simply a function analytic everywhere in the complex plane, that function is called entire. That function is called, which means every point in the complex plane is analytic, that function is called entire function. Now constant function is differentiable and the constant function is analytic, it's analytic everywhere. But here we are collecting our set v equal to f is non-constant entire function. So for example, f of z equal e power z and g of z equal to z. A lot of functions are there. Just giving example for f of z, g of z. These all those elements belongs in the v. So let f be a non-constant entire function means f should be e power z or z and polynomial or sin z or cos z, whatever the non-constant analytic function. That is an arbitrary on f. We don't know which f in the v. Just take random f in v, random element in f. Sorry, you take random element in v. From that element always has this property or this property. Suppose some f has this property, some other f does not have this property, then this option is not true always. Okay, you take any random f always has this property, then this is true. Now we have to do the problem. Okay, before when we going to do the problem, I have to give some theorem statement. From that theorem statement, we can conclude all those options. So I explained what is the meaning of entire. Now I am going to give the properties of entire function. Picard's theorem. Picard's theorem. A non-constant, just write the statement. A non-constant entire function omits at most one point or a non-constant entire function means any non-constant entire function f, any non-constant entire function f omits at most one point. What is that meaning? Come on please madam, is there any question? Okay, so that is image of f could be c or c removed some z naught, that's all. Not equal, f could be this or f could be this. That is the meaning of that sentence. Here, I wrote here, no? Any non-constant entire function f omits at most one point. At most means it could, if it is omit, if it is omit, 1 point only omit, not for 2.3 point. Okay, at most means it could be omit or cannot be omit. Okay, if it is omit na, like this, we don't know, some point in the codomain does not have a pre-image. What is this meaning? Image of f equal to onto means image of f equal to c means onto the range set equal to whole set in the codomain. Okay, this is a theorem number 1. Another one more theorem, open mapping theorem. Just open mapping theorem. Open mapping theorem. Open mapping theorem. This is a Picard's theorem. This is a little Picard's theorem. Okay, anyway, fine. Any non-constant entire function, any non-constant entire function maps open sets to open sets to open set. That's it. Only 2 theorems enough. Open mapping theorem means if it is non-constant, it carries open set to open set. If we are giving input in the open set, whose output again a open set. But same open set not necessarily. Identity function, if it is giving any open set, the same open set it will be outcome. But some other non-constant, generally non-constant entire function, if it is given some open set, na, the output it could be somewhere the open set in the codomain. Okay, it carries open set to open set. Input is open, the output is also open. Maybe input is a smaller set of open set, the output it should be bigger open sets when the size. Okay, anyway, fine. These are 2 theorem. From that theorem, try to conclude. Only 2 theorem is enough to solve all those problems, all those options. Now you have to respond your answer, please. This is a hint for 2 theorem to solve, please. Image of f means just image of f equal to.
By open
yes,
mapping theorem, A is correct. So this is the response.
Okay, very good. By open mapping theorem, yes, madam.
A is correct. The other person, GV, option A and C are the answers.
Okay, very good, madam, very good. Now E is an open set by f be a non-constant entire function by open mapping theorem says that any non-constant entire function maps open set to open set. By according to open mapping theorem, this is always true. Any non-constant entire function, this carries an open set to open set. It's a correct answer for A. What about this? Suppose if it is a, if you fill B option is failed, you have to give one counter example. Counter example in the sense you have to find some non-constant function whose range set, whose image E intersection with this is non-empty, then this option is wrong. F of z equal to z is identity function, is a non-constant entire function whose range set is again image of f equal to whole complex plane. Now this is a set of element collect in C such that whose modulus value is less than 1, which means is an open unit disk. It's an open unit disk intersection with open unit disk. This is clearly non-empty. Why? Open unit disk also in C. So intersection is another open unit disk again. But this option says that I have a sum f violating these options. So therefore not true for all element in V. So therefore this option is not always true. Not always true. Okay. Fine. Now I would like to ask one question. I have an example, this option is false. Now the question is, this option is always false. This option is always false. To take any non-constant entire function, image intersection this open set is empty. This is always false.
Yes.
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 So very good. So very good. Always false, sir. Aishwarya. That Manivannan. Very good, Manivannan. It's always false. Why? In the sense, here, just you can use Picard's theorem. Any non-constant entire functions will meet at most one point. So therefore, whose range set is this, or this, or this. Now, here, this will be always there. But whose range set is C removed some Z naught or C. When intersection, this is also non-empty. You have to intersect with the unit disk. You have to intersect with the unit disk. Again, non-empty. Why it is non-empty? This is the only single point removed. But the Z naught, it could be in the unit disk also. But the intersection is always non-empty because this has uncountably many elements, but this only removed a single point. So this intersection also always non-empty. This intersection also always non-empty. Because image, it could be C, intersection is non-empty. Image could be removed single point only in the whole complex plane, still whose intersection is non-empty. So therefore, always you take any element in the F whose intersection is always non-empty. But here says that empty, but that is false. Once B is false, oh, that's all. Okay. B is false. B is always false. What about C? E intersection R is non-empty. Yes, clearly. Why? E could be C or C removed some Z naught. Whose intersection R, this is clearly non-empty. Intersection is R, so clearly non-empty. Why? This is an uncountable set and is a subset of C, but only element removed is Z naught could be R, but intersection is always non-empty, not necessarily intersection R. But here intersection is always R, but here not necessarily intersection is R, but intersection is non-empty. So therefore, this option C is always true. What about E? What about E? So E is also false. Why? Why means here, according to Picard's theorem, says that whose E equal to C are removed singleton point from the C. This is also unbounded set, and this is also unbounded set. So either case, image always unbounded. Either case always unbounded. Very good, Manivannan. Leoli's theorem says that if E is image is bounded entire function reduced to constant, but given the function is non-constant, so that is also not possible. We can say that way also, but we are using here only two theorems. From the two theorems only, I am removed. If you know the Leoli's theorem, bounded. Suppose option D is true. A non-constant entire function whose image is bounded, that or we can say like that. We have to say proper way. So bounded entire function. I have an entire function. I don't know whether it is constant, non-constant. I don't know. Just I have an entire function whose image set is bounded. Entire and image bounded. From both the things, concluded that F should be constant. I am not saying. Leoli says that is a Leoli's theorem. Bounded entire function reduced to a constant. Okay. But our hypothesis F is non-constant. Therefore, non-constant entire function image not necessarily never could be bounded. Never could be bounded. Non-constant entire function image never could be bounded. So therefore, this option is always false. The only option is A and C. Is there any question, please? Is there any question? Okay, madam.
Yes, sir. Yes, sir.
Okay, madam. I can move other problem. Okay. A simple problem. And interesting, easy problem also. Another one more problem we can do. In exam, this kind of problem is very simple to work. Only few minutes only, few minutes in the sense it will take only few seconds. It depends on person. Just think and applying whatever studied and recalled, just applying. That's all. Okay. Another one more problem, we can do it. Okay. Another concept theoretical problem. It's an interesting problem. Let f be an entire function. Which of the following is true? Which of the following? Option A, f is constant. F is constant. If the range of f is contained in a straight line. Option B. F is constant. If f as uncountably many zeros, option C. F is constant if f is bounded on set of all z and c such that the real part of z less than or equal to 0. Option D. F is constant if the real part of f is bounded. Real part of f is bounded. This is a question. Please read the question. Please read the questions. What is given? Again, they are giving just the entire function. We know entire means f is analytic everywhere in the complex plane. That function is called entire. Just they are given random entire function. When the random entire function is satisfying this problem. First option says the random entire function whose image is contained in a straight line. That random entire function is the random entire function should be constant. If means this is a given hypothesis. This is a general hypothesis, and this is that f has this property. This implies that f is constant. That is the meaning. Again, that entire function has this property. This means what is that meaning? If means p if q or whatever it may be. Q if p means
the response from the participant. Option C and D are correct.
Option C and D are correct.
Yes, sir.
Okay, we will check. Okay, madam. No problem. We will check. Anyway, so I'm trying to explain what is the meaning of the question. First, we need clear about the question. What is the asking? Otherwise, we can't understand the question. Then how we can reply the answer? So we can randomly reply. That could be correct or wrong. We don't know. Whenever any exam, any competitive exam or whatever the exam, the question first you should understand what they are asked, what you want to do. Okay, most of the people they couldn't concentrate with the question. Then they will do the options. Then finally, when the result is coming as some option is wrong, then they, oh, I didn't see that option. I didn't see that given that conditions, all those things happens. Okay, anyway, fine. I try to explain this meaning. Q, if P means P implies Q. This is a hypothesis. From that hypothesis, we can conclude Q. What is your P statement? What is your Q statement here? Given F is general entire function, we don't know. This is your P statement. If the range of F is contained in a straight line, this implies constant. Same thing here. This is your P statement. Once you know the P, from that P, we can conclude Q. So F is a non-counted entire function. As uncountable many is zero, then F should be zero. This is a hypothesis. If we can conclude or not. The same thing. F is bounded on this set. From that things, we can conclude F is constant. Similarly, the real part of F is bounded, then F is constant. Is there any idea? Any idea? Somebody's said answer. Yes, madam.
All the options we use Liouville's theorem. So this is
all the options we can use Liouville's theorem. Liouville's theorem. No, madam. That is not correct. We can use some other theorem, but somebody said we don't want to use the Liouville's theorem. If it is bounded, then we can use Liouville's theorem. But anyway, I try to explain. So we know F is an entire, okay? Entire two pieces, constant and non-constant. Non-constant entire. Entire function two cases, constant entire, non-constant entire. Constant entire means this gives only output f of z equal to some k for all z in C. Okay. Non-constant entire means, by the Picard's theorem says, image of f could be C, or image of f could be C, or C removed some z naught. See, entire function, two types of entire function. Here, actually, entire function, transcendental entire function is there, transcendental, non-transcendental entire function. That is different story. But I am trying to explain here entire function, constant entire function, non-constant entire function. Constant entire function image means just a single point whose output. Non-constant entire function means whose image is a non-constant entire function whose image, not means just whose non-constant entire function whose image look whole complex plane or removed some point in the complex plane, some point, single point only. Now from that things just to conclude. So f is an entire function whose output, f is an entire function whose output whole complex plane, or from that complex plane I removed just some point, that's all. Means remaining things are. This is a behaviorism. Or some point in the output. So picture number 1, picture number 2, picture number 3. What the picture number 3 says that f whose range set is only single point, or range set the whole set, or range set is removed only single point, means all other points are. So what the option says that the range of f is contained in the straight line. It is possible. This is not possible. Why? This is not possible in the sense f should be whose image lying in the straight line. If it is whose image lying in the straight line, it omits more than one point. Correct? What the Picard theorem says, if the image omits at most one point, it could be omit or not necessarily to omit. Omit means at most one point omit. But if the straight line only the image, whose image is lying in the straight line, how many points it could be omit? Uncountably many points omitted, the entire function. More than one point omitted. Therefore, if omitting more than one point, then what we say that the f should be constant. That first option says this is not possible and this is not possible. Only they said this is the whose output only lying on the straight line like that or this. Okay. What this says that this is our complex plane whose output, suppose they are lying only some line, we don't know, it could be here or here, only suppose whose image is lying in the line, it could be omitting more than one point. Omitting more than one point. If it is omitting more than one point, that f should be constant by Picard's theorem. Picard's theorem says that omit more than one point, that f should be constant. Okay. Therefore, this option, range set is contained in a straight line whose range set is contained some straight line which omits, the image set omits more than one point. Therefore, that f should be only constant. Therefore, that f should be only constant. Therefore, this is option A, always true. Option A, always true. What about B? F is constant if f has uncountably many zero. Uncountably many zero. What is that meaning? Said okay, I will explain B option at end. Now we have to conclude C and D. Then we will work with in the B option. Option C, f is constant if bound on the real part. F is constant if the real part of f is bounded. So what is that meaning? The real part of f is bounded means f going from complex plane to complex plane. Real part is bounded means real line, it could be somewhere. It's a bounded. Open or closed, whatever it may be. So image could be lying only this. Why? Yeah, this option C, option D says that whose real part of f is bounded in the sense real part is a real line, it's a bounded. It could be like or like here also maybe. Okay, the real line it's bounded or union of some other bounded set, union also bounded like that. So whose real part is bounded, then what happens? It omits more than one point. It omits more than one point. So therefore, f is constant. Or given the statement also, so any any entire function whose real part bounded or real part constant or imaginary part bounded, imaginary part constant, and whose image is lying in the line, or whose image is lying some arc, or whose image is some portion of the complex plane, all those things are implies f should be constant. F should be constant. So given analytic function, given entire function whose real part is constant, then f is constant. That is a theorem, standard theorem. You take any complex book, this theorem is standard. And imaginary part is constant, that function should be constant. That entire function should be constant. Entire function, if it has this property, then the entire function implies this. F is entire whose real part is bounded, then f is constant. F is entire whose imaginary part is bounded, then f is constant. F is entire or real and whose imaginary and real part as either one of them bounded, then f is still constant. Whose image of argument lying in the line, that f should be constant. So a lot of things are there. Okay, anyway, from that theorem implies that, or you can draw the picture like this, whose real part is bounded, real number bounded in the sense there is a sum. Real part is bounded in the sense from C to C, whose output somewhere real line. That's all. Whose image lying only this portion only, which means omitting more than one point by Picard's theorem. Therefore, f should be constant. Okay, the real part of f is bounded, which implies that f is constant. Or imaginary part of f is bounded, then f should be constant. So option D is always true. Option D is always true. Is anybody know about C? C is true or false? Yes, madam. Mic is open.
Option C and D are correct, sir.
Option C and D are correct. Anybody answer response? Option C is correct. No. Just to think about. I would like to explain right now. Just listen. That is very careful. Okay. Just to see. Okay. Now, suppose if true means to take non-constant entire function whose f is bounded on the real part, that should be constant. You have to prove. Or if you feel option C is wrong, you have to give one example of entire function which is non-constant, but this property has, but does not imply constant. Okay. Now I am going to try to give e power z. What is the meaning of if you know, right? F of z is a e power z. That's a standard entire function from C to C whose image removed single point. The image does not take zero value. Okay, anyway, fine. What the question asked, real part of z less than or equal to 0 means this is a madam, someone mic is open, it will make disturbance. Okay. So this is a left top plane. This is a left off plane. Okay, left off plane. The question less than or equal to 0. Suppose I have a entire function. Range of the left top plane is bounded, which implies f is constant. That is a question. This is the set. The set is left top plane. F takes the left of plane, image of f of left of plane always is bounded. That's the meaning. Bounded. This implies that f is constant. That's a question. That is a question. I said that answer no. Answer is no. Not necessarily constant. Not necessarily constant. Not necessarily constant means I would like to give an example. Now f of z equal to e power z. E power z I can write e power z x plus iy. X plus iy. Just I can write e power x into e power iy. E power x into e power I. Now what is the mod f of z equal to modulus of e power x into modulus of e power iy. Now you take modulus e power x into e power iy. So you know e power I theta whose modulus value is always 1. Why? Cos theta plus I sin theta. Take modulus cos square theta plus I sin square theta, which is equal to always 1. Therefore, e power I theta always 1 for any theta. Okay. So therefore, e power iy value is always 1. E power x, it takes always the positive value. So therefore, only e power x only become. E power x is a positive value. When you take modulus, is still positive. So instead of modulus, I can take only e power x only, because e power x always give me positive. So e power iy, it could be 1 only. So f of e power z equal to e power x. Fine. So what can you say about here? This is our left top plane. In the left top plane, all real part is negative. Real part is negative. When we apply real here, now f of x plus iy going to just e power x. Right? Is that equal to x plus iy? F of x plus iy equal to just e power x. Where when we take modulus, otherwise we can't say. When we take modulus, so in particular, if you take any element in the left top plane, not only left top plane, take any complex number z, when you're applying modulus, the output is e power x only. Okay, fine. So here when we check left half plane, you take any complex number x plus iy whose output only x only, e power x only. So here it will be negative complex number. Negative in the sense real part of f of s is less than or equal to 0 means all x are here negative. So minus x plus iy, which implies that e power minus x. E power minus x always bounded. Where? In the real part. When you write the e power x graph, it's like this. Okay. When the negative part, e power is bounded by 1. So therefore, this is bounded by less than or equal to 1 for every element belongs to left half plane. E power it is bounded by 1 in the left half plane. Okay. I have an entire function as this property, but that does not imply f is constant. Okay, therefore this option is not true. This option is not true. I have an entire function as this property. Left half plane whose image is bounded in the left half plane. But f is not constant. E power is it is we know, no, it's a non-constant entire function. And entire and this property does not implies always constant. Okay, that is the example. That example is counter example. Therefore, this is not true always in option C. Did you getting my point, please? Somebody said right. C option C is correct. C is false. Is there any question from C? Please. Is there any question from C?
No, sir.
Okay, madam. So now we have to work with B option. Now we have to work with B options. Please, whatever I said, you write. It is useful for to solving problems. More problems asking from that entire function and Picard's theorem only. Okay, try to understand the concept. Anyway, now I am going to write some hint and solve this option B. Uncountably means 0. Okay. Zeros are isolated, you know. Uniqueness theorem, you know. Identity theorem, you know. So two theorems are there. Just written. It will be again the theorem. We can use some other problem also. Okay. Uniqueness theorem. Wait a minute. I will write that statement because we can solve some other problems also. Frequently it will be coming. No. Wait a minute. I will write the theorem statement properly. Just write uniqueness theorem. So zeros where the uniqueness theorem. Wait, I will write. Yes. The theorem should be noted because this is very important. If I write something, maybe if I missed something, it will be misleading. So anyway, always you can write in the classroom the theorem and definition. You should see the book and write. Suppose if we are missed something, then it will giving misleading. Suppose f of z is analytic. F of z is analytic in a domain D. And Zn is a sequence of distinct points converging to a point is that not in D if f of Zn equal to 0 for every n, then f is identically 0 throughout D. Do you understand? See, another one more theorem also there. I will write that will be to solve next and problems. Uniqueness theorem. This is a uniqueness theorem. What the theorem said? Suppose f is analytic in a domain D. Domain means open connected set. We don't know. Just for example, this is an open connected set at D. This is open connected set D. Suppose f is analytic in a domain D, and Zn is a sequence of points. Some sequence of points. It's converging. Here I will write. So D, it's an open connected set. Zn is a sequence of points. Suppose that sequence converging to Z0. There is a sequence. Zn is a sequence. Zn is a sequence of points converging to some x0. Each points are distinct. So Zn is a sequence of distinct points converging to a point Z0 in D. If suppose f of Zn equal to 0 for every n, then f is identically 0. That is the uniqueness theorem says. Suppose f of Zn equal to 0 for all n, this implies that f is identically 0 throughout on D, every point. The thing is that I have an analytic function. See here, I have an analytic function. This analytic function Z1, Z2, Z3, Z4, and so on, all Zn's are zeros. So root of the f. All Zn's are root of the f. When applying a point from Zn, that f killing, which means if you take an element from the sequence, applying f, that f vanished. So roots Z1, Z3, all of them roots of f. Suppose this roots of element is form a sequence. The sequence suppose converging in D itself, not outside D, within D itself. It could be converging here, or it could be converged here, it could be converged here, or it could be converged here within the D itself. Zeros of f. All these elements are called zeros of f. The zero sets, zeros of f, the sequence as this limit. The sequence, suppose the sequence converges to some Z0, then f should take what is the value of f. This is my picture. This is some girl or boy, whatever it may be. This is some S girl. That I call this girl name. Yes. Any participant, please come. What is the f of s? What is the output of s? Participant, please. I have an analytic function in the domain D. Analytic function has this property. What property? There is a sequence. All the elements in the sequence f vanishing, and also the sequence converging within D itself. This is a given property. Now I would like to ask, what is this girl? Just I draw some picture. Just I call that picture S. Now what is the image of this S? Please, someone, participant. Please, someone participate. Come on. Come on. It's a super nice problem. Interesting problem also. So each and every mathematics images vanishes.
Image vanishes.
Wow, very good, very good. What is that? Why? Why images vanishes? Why? Come on, Nakesh and Nisha something said. So very good. He or she they understood very clearly. Why? Just right? Why? Why image vanishes?
We have the property.
We have
That's what we
very good, very good. We have the property. According to the theorem says that. Wait a second. I will come. Madam, wait 1 second. I will come.
Yes, sir.
Yes, please. Yes, according to this theorem says that if any sequence vanishing, any sequence vanishing all those points f, and unfortunately this f converging this domain itself, then this theorem says that f of there is a sequence f of zn equals 0 for all n, means f of z1 0, f of z2 0, f of z3 0, all these points in the sequence. So vanishing, then f should be 0 throughout D. This is a uniqueness theorem says that. According to uniqueness theorem, this girl whose output is 0 only. Not only this girl, you take any picture of this. Just I would like to ask first thing. Now this is some bird. Yeah. Now ask me a question. This is some S1 picture. Now what is our f of S1? The same answer. Why the same answer? If the vanishing only for at least vanishing in the sequence every point and the sequence converging some point in the Z0 itself, in the D itself, then f vanishing throughout D. So therefore, image of S1 also 0 only. Okay, image of 0 only. Right? So lot of problems are there involving this theorem. I will do next theorem. So next problem I will do only one theorem to conclude all those options. Okay, locally f is analytic in a domain D. F has a 0 sets. F has a what are the elements root of f in the D? You collect all those elements. That is called some set. Yes, the set S, if it is as some limit point, that limit point in D, then f is throughout takes zeros. F is analytic in a domain D. F as 0 sets, which means some point of in D is root of f. We collect all those points. What are the points root of f? To collect all those points, that is form is some set just called S. This set as a limit in D, the set S as a limit in D, then f vanishing throughout D. Okay, here indirectly they are giving this is a sequence, this is a zeros of your f, this zeros of f as a limit in D, that f has 0 everywhere, just a 0. Okay, anyway, fine. I'll write another one more theorem. I will write here another one more theorem, just interesting theorem. 2 theorem, then we can solve a lot of problems in the CSIR problem. This is the backbone of the complex analysis running. Okay, wait, I will write identity theorem. Everyone should know, try to understand identity theorem. suppose f of Zn is a sequence of points. F Zn is a sequence of points having a limit point in D if f of Z and g of Z are analytic, f of Z and g of Z analytic in D with f of Zn equal to g of Zn for every n, then f is identically g throughout D. Please see here. It's a very important theorem in the complex analysis. This is a uniqueness theorem. If function has this property, why they call the uniqueness theorem means f has this property, then f should be 0. That will 0 function is unique. They call uniqueness theorem. Here come to uniqueness. From the uniqueness theorem, they are deriving the identity theorem. Without uniqueness theorem, we can't say the identity theorem. From that uniqueness theorem, they are introducing identity theorem. How they are introducing here? Zn is a sequence of points having a limit point D. If f and g are analytic function D with this property, then conclude that f equal to g throughout D. Now I would like to ask one question from the participant. Please, anyone come to give the answer? Come on. Okay. Please, participant. This is my D. Okay. I would like to write here. It's an important theorem. So, okay, now I have a picture. This is my D. D means open connected set. I have D. Okay. I should draw some diagram. I draw some animals. I'm not very good draw. To conclude anything, I don't know which animal I said, but this is just roughly. This is your D. That animals in the D, F and G are analytic. Okay. So there is some function. Not there is a function. There is some sequence. This is your sequence. Zn is your sequence. Now, f of Zn equal to g of Zn for all. If g are analytic, and f of Zn equal to g of Zn for every n. F of Zn equal to g of Zn. Okay. Now, what is the output of this? Is cow. I don't know. This is not cow, just a written, but I am writing very bad drawing. Cow means just some hedge. I call the set hedge. Hedge means hold the set in cow. Now the question is, what is your f of h equal to g of h? Is it correct or not? First thing, yes or no? D is a domain, f and g are analytic, and both the functions, they are agreeing in the sequence. Zn is a random sequence. In the domain, they are agreeing in the sequence. That's all. F, G are analytic and D is a domain, and some sequence Z1, Z2 are sequence. F and G are agreeing each point in the sequence. Now they are agreeing every point the set curve. Every point in the element in the curve, it is agreeing. F of H is equal to G of H. What is your answer? Please, any participant? Come on. Anyone? Means you have doubt? Very good, GV. Very good. What is that meaning of this? Krishna Priyava. Krishna Priya. Very good. Yes, sir. Very good. Nice. Nice. Okay. Okay. Kamavati Singh Sivasankaran. Yes. Why? Please try to explain. Type, please. Kamavati Sivasankaran, please type. Why this is true? Most of the people, they said answer. Only one participant they have clearly mentioned. Remaining people, yes sir, yes sir. F and G are identically throughout. Very good, very good. Okay. So according to that identity theorem says that there is a some sequence, two functions are agreeing in some sequence, each point in the D, then they are agreeing in the throughout D. They are agreeing in the throughout D. F is agreeing, F and G are agreeing these points of Zn, then F and G are agreeing throughout in D, in particular agreeing on this picture. Is it correct? See here, see here. Suppose Zn is a sequence of points having a limit point in D, that is a matter. Limit point in D, F of Z, G of Z are analytic in D with as this property for each n, then F and G are throughout in D. The thing is that Z1, Z2, Z and so on, it will be stopped here only, not for going outside. So therefore Z1, Z2 is a sequence whose limit is this. Suppose if you going like this in the outside, or if suppose if you go like this is our sequence of points Zn. Now what is your conclusion? Come on. What is your conclusion? What about your conclusion? F of H is equal to G of H. Please. Please. Please come on. No, sir. We can't conclude. We don't know. Yes. Yes. The sequence, it could be converging outside also. Because D is open. The limit point, it could be outside. That will be not guaranteed that inside. Okay. The limit point, Zn is a sequence which converging a point, that point should be inside. That's the meaning. Suppose Zn is a sequence of points having a limit point in D. There is a sequence whose limit point in D. Then suppose two analytic functions are agreeing on the sequence, then F and G are agreeing on the whole the set. So it will be converging somewhere within D. F and G are agreeing in the sequence. From that identity theorem, F, G are identically same on whole D. In particular, F and G are identically in this picture. This is term picture. Okay. Anyway, so okay, this is identity theorem and this is a uniqueness theorem. From that theorem, we can I will do next problem. So I written the statement here: identity theorem and uniqueness theorem. Okay, uniqueness theorem says that F is analytic in a domain D. There is some sequence F vanishing every point in the sequence. The sequence has a limit in D. Then F is identically 0. Okay. From that theorem, H of Z they are defining like this. This is the proof, very simple. H of Z equal to F of Z minus G of Z F is analytic and G is analytic. The difference is also analytic. H is analytic function in D. H vanishing on the Zn. Just applying f of Zn equal to h of Zn equal to f of Zn minus g of Zn. And f of Zn, g of Zn are agreeing. So k minus k it will be 0. H of Zn equal to 0 for all Zn, and Zn having limit point in D. According to this theorem, H is vanishing some sequence of points, that sequence converging in the domain D. According to this theorem, H is identically throughout 0 and D. Once H is identically throughout 0, f of z minus g of z equal to 0, which implies f of z equal to g of z for all z. That is the proof of that theorem, identity theorem. Okay. Anyway, now come to our option B. F has uncountably many zeros. Just you take a result. I will explain this two theorem next problem it will be using. Result. F has uncountably many zero. So for example, S is a set of all z in C such that f of z equal to 0. This is uncountable. Assume that uncountable set. Any uncountable set as a limit point in the set. Uncountable set as a limit point. The set itself. Any uncountable set as a limit point in set itself. Okay, that could be R in R2, R cube, and so on, R in C. Any uncountable set as a limit point, the limit point in the set, within the set itself. Okay, from that conclusion, F has uncountably many zeros, which means just I call that zeros of F, I call that set S equal to set of all Z and C such that F of Z equal to 0. This is an uncountable set, and this is zeros of F. This zeros of F as uncountable set. This theorem, this result says any uncountable set has a limit point. So therefore, S has a limit point. Now, what is your conclusion? What is your conclusion? S equal to S has uncountably many points. This has element in 0. Now what is your conclusion? What is your conclusion? This is your uncountable set. We don't know which uncountable set. F has uncountably many 0 in D. This is your D. Zn is a sequence. That sequence converges. This is uncountable set. From the uncountable set, I can find okay, wait, I will explain. This is an uncountable set as a limit point some Z0. That is, there exists a sequence. There is a sequence Zn in S uncountable set such that S in the set such that Zn goes to Z0. F is analytic and f of Zn equal to 0 for all n. And a limit point also in S, which implies that by uniqueness theorem says that there is a sequence which converging in the point, every point in the sequence f has value 0, then f is identically 0 on throughout D. Okay, therefore zero function, f is a zero function. Zero function is a constant. Therefore, option B is true. Option B is true. Are you getting my point? Are you getting? F has uncountably many zeros means the result says any uncountable set has a limit point. One, suppose just I call that limit point Z0. Z0 the limit point, then there is some sequence Zn in S from the zero set. There is a sequence Zn in S such that Zn goes to Z0. And the zeros of F f of Zn equal to 0 for all n, which implies every element in S is zeros of f. Therefore, f of Zn equal to 0 for all n. By uniqueness theorem, f is 0 throughout in D, which implies that f is constant. F is a zero function is a constant. Therefore, option B is also correct. Option B is correct. What are the answer for this question? What are the answer for this question? I think now you got idea. Okay. Next problem I'll try to use identity theorem and uniqueness theorem. Madam, is there any question, madam?
No
Still
question,
no.
sir.
No question. Madam, are you okay with this?
Yes, sir.
Okay. Madam.
Now again your board is low, sir.
Sometimes this is
Yeah,
this
now it's
camera. This camera depends the face. When the face, it will be focusing. Without, if I rotating, like if I turning this side, it will not focusing. Camera people setting like that. Okay, anyway, madam. So again, this problem number 3 or 2, I don't know, 3, I think so. Let f be analytic. It's a simple, easy, interesting problem. Analytic function defined on the open unit disk in C, then f is constant if f is constant if f of 1 by n equal to 0 for every n greater than or equal to 1. B option. F of z equal to 0 for every mod z equal to 1 by 2. F of 1 by n square equal to 0 for every n greater than or equal to 1. Option D. F of z equal to 0 for every z in -1 to +1. The hint only for uniqueness theorem, identity theorem, then you can use. From that, you can conclude, please. So what is given? F is analytic function defined on the open unit disk. F is analytic function defined on the open unit disk. Okay, just assume that this is an open unit disk. Okay, just assume this is an open unit disk. So 1 unit radius. Okay, defined analytic function. So which of the following options imply that f is constant? This is a given. Suppose f is analytic as this property, which implies f is constant. F is analytic, f of z equal to 0 for every element in the set, which implies f is constant. F of z as this property, which implies f is constant. F of z is analytic and f has this property, which implies f is constant. Please. Come on. It will be very easy only. Come on. Come on. Kannata D. Waha. G. All are correct. Suganti A. D are correct. Indu all. Come on. Wow. Okay. Can I solve right now? Okay. I'll solve right now. Now, so given option A, what is the meaning of option A? F of 1 by n equal to 0 for every n greater than or equal to 1. Actually, this is not valid when n equal to 1. Why? When n equal to 1, f of 1. But f is analytic defined on the open unit disk. Open unit disk means they are inside only, not for the boundary. But they are given. But don't worry about anything. So you can remove from 1. You can start from 2. Okay. You can start from 2. This is a natural number, no? Okay, anyway, fine. It says that f of 1 by 2, 0. F of 1 by 3, 0. F of 1 by 4, 0. And so on. 1 by 2 here, 0. 1 by 3, 0. 1 by 4, 0. 1 by 5, 0. And so on like this. F is analytic function as this property. Whose zero set is this. What is zero set? Zero set, I call this a zero set means just I call it set of all Z in C such that f of z equal to 0. This is zero set notation. Now your zero set is given. Your zero set equal to 1 by n such that n greater than or equal to 2. 1 by 2, 0. 1 by 3, 0. 1 by 4, 0. 1 by 5, 0. All those things. Now, what is your conclusion? What is your conclusion? Okay, now I would like to say I have a zero function. G of z equal to 0 function. This is analytic function. This is analytic function. And g of z equal to 0 for all z in the open disk. In all the open unit disk. Okay. Now, f of 1 by n equal to f of 1 by n equal to g of 1 by n. For every n greater than or equal to strictly greater than or equal to 1. F and G are agreeing, right? F is also analytic, G is also analytic. Given F is analytic, now I take G is zero analytic function. Zero is also constant function, all constant functions are analytic. F analytic, G analytic, two analytic functions are there agreeing on the set 1 by n. 1 by n. Okay. 1 by n is a sequence. That is f of zn equal to g of zn. They are agreeing. Now zn goes to some z0 in the set D itself. Now zn equal to 1 by n. 1 by n converges to in the unit disk itself. 1 by n converges to the unit disk itself. I have a f and g are analytic function in the unit disk, and there is a sequence 1 by n. On the 1 by n, f and g are agreeing. F output and G output also are same for each n. That is called f of 1 by n equal to G of 1 by n. Okay. Okay, fine. From that conclusion, what is that theorem? Identity theorem. Both f and g are agreeing on the 1 by n, and 1 by n is a sequence. The sequence has a limit point in D, open disk in D. By identity theorem, f and g are identically same. F and G are identically same. F of Z equal to G of Z for all Z in the open disk. This implies that F is only zero function. From the conclusion, F has this property now, then F is only zero function. Zero function is always constant. Therefore, option A is true. F is analytic. F has this property now, then F should be zero function. That zero function implies F is constant. Is it clear? Is it clear? Okay. Option A true. What about this? What about this? What is the meaning of B option? B, there is a half radius circle. This is half radius circle. F is vanishing every point in the circle, half radius circle. We don't know this point. Now the question is, I would like to ask one question. I would like to ask one question. This is some bird B. I call bird B. Okay. Now what is your f of B? Come on. I know only f vanishing only off in circle. F every point takes zeros on the circle itself. That's all. Now the question, what is your image of this? Hindu 0. Aha. Aha. How? How? Karnatal 0. Aha. Come on. Come on. How? F analytic function vanishing on the off radius circle only. Uniqueness theorem. Aha. Good. 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 Is point out. Next. 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 Come on. Next. Okay, anyway, fine. So what is the image means? 0 only. What is image means? 0 only. Why? Why? I will explain. I will explain. So now we don't know. This is our f, just f function. Now I have taken 0 function, g of z, and g of z equal 0 function. Okay, identity. Very good, madam. G of z is a 0 function. F is a just analytic function. Analytic function has this property. F is analytic as this property from that property which implies constant or not. We are going to check. Okay, before going to check, I take g of z equal to 0 function. Now f has a property. What property f has? Every point in the off radius circle as 0. Okay, in particular, every point you take any point. So in particular, now I can able to find a sequence Zn on the circle Z1, Z2. It will be converges to 1/2. I can able, or here also we can take this is a point. This is Z1, Z2, Z3, Z4, all those points. F taking every point in the circle 0, in particular each point in the sequence also taking 0. That is I called Zn. Now f of Zn equal to g of Zn. G of z is a 0 function, so therefore g of Zn also 0. F already every point in the circle 0, in particular Z1, Z2, I take the sequence, I construct the sequence Z1, Z2, Z and so on converges to 1/2. So F also 0. So F of Zn equal to G of Zn for every point in the Zn. Also Zn converging only within D itself. D is an open unit disk. Zn is converging within D itself. By identity theorem, F and G are agreeing on the sequence of points. The sequence has a limit point in the D itself. By identity theorem says that F and G are throughout identically equal. F and G are throughout identically equal, but unfortunately our G is 0 function. This implies that F should be 0 only. F has this property na. From that identity theorem that F should be 0. Now the 0 function is constant. Of F analytic as this property is implies that F is constant. So option B is also true. Now what about C? Similar same concept. So open unit test 1/n square like this. This is the zeros of F. The sequence converges to 0. Or you can use identity theorem. 1/n square goes to 0, and also f of 1 square equal to 0 for every n. this implies that f is identically 0 on D throughout D. Okay, f should be taking only. So f analytic and f has this property now, f should be 0 function only, 0 function should be constant. Therefore, option C is also true. What about this? What about this? What about this? So minus 1 to plus 1, minus 1 to plus 1. Every point in that interval, f is 0. Every point in this interval, f is 0. In particular, f of 1 by n also 0. For n strictly greater than or equal to 2. N greater than or equal to 2. 1 by 2, 1 by 3. So every point in the line, f vanishing. In particular, 1 by 2, 1 by 3, 1 by 5, 1 by 6, 1 by 7, and so on. All these points also 0. Now f vanishing 1 by n, and also 1 by n goes to 0. F 1 by n also goes to 0. By uniqueness theorem, f is identically 0. By Zn goes to Z0, f of Zn equal to 0 for every n, then f is identically 0 by uniqueness theorem. Or you can use identity theorem also. When using identity theorem, you have to construct a G. Here G function is 0 function. You can use identity theorem or uniqueness theorem. Both of the theorem you can use. Any one you can use. So 1 by n goes to f of Zn, 1 by n goes to 0. So therefore, f of n vanishing for every n, which implies f is identically 0 throughout 0. So f is throughout equals 0, which implies f is constant. So this all the options are correct. Is there any question, please? So finally, what is the guess of this B? So okay, I will ask one question. Okay, this is our open unit test. F vanishing this arc. I don't know this arc. F vanishing this arc. Here, f of z equal to 0 for every element in the arc. Now, what is the image of this bird? What is the image of B? What is the image of B? Just I have an analytic function. Vanishing every point here only. I don't know remaining place whether it is vanishing or not. F is analytic and F vanishing only this side, which implies that F of B we can't save. We can save something else. What?
We can't say.
We can say. Just think. Still, you are not understanding this theorem. You are not understanding. Please try to read the theorem, recall and recognize. Come on. What is the given information? F is an open unit disk. My F has this property. What property? Every element as in the arc vanishing. That's all. Now the question is, what is the image of B? B is some bird, just a written. What is the image of bird? Identically 0. Very good, Suganti madam, I don't know. So okay, so Suganti madam written that image of this set also 0. Why, Suganti madam? Okay, in the I try to explain okay, I try to explain everyone. So this is a 0 set. This is a 0 set. you can construct a sequence, just a sequence Z1, Z2, Z3 and so on. Some sequence you can construct which converges to here itself, Z0. Now f of Z1, Z2 vanishing. F is vanishing on this curve. In particularly Zn is a sequence. Just I constructing sequence. Zn is a sequence. Every point in that sequence f vanishing. Okay, by uniqueness theorem says I have a sequence Zn. I have a sequence Zn which converging point in the Z0. I can able to construct a sequence that is a point. That is a point. Why? This is uncountable set. This is uncountable set. Before also one written any uncountable set has a limit point. If zeros of uncountable set, f has a zeros, collect all those zeros. Unfortunately, the set uncountable, then f identically vanishing all those points. Here I said this is uncountable set. I can able to always construct a sequence. Uncountable set has a limit point. Just you can somewhere you can mark that limit point, which means there is some sequence which converges that point. Now f of Zn equal to 0 for all points y. So f is vanishing on this arc. In particular, any points in the arc also vanishing. So f of Zn also 0. By identity theorem or uniqueness theorem says that Zn f of Zn equal to 0 for all z and Zn converging some point, then f is identically 0. Once f is identically 0, in particular f also taking 0 only here. So that is why f of b equal to 0. This is a concept based. Okay, to try to understand all the theorems like that, we can do every theorem. We can understand, we try to explain how the people whether they could understand or not. Okay, anyway, fine. I will do the problem. Okay, now what is the answer for this question? All the answers are correct. Now I will do some other problem. Is it okay? Is it okay? Okay, madam. So again, I am saying how many problems we are going to solve doesn't matter. Lot of problems are there in the YouTube channel.
There is a
yes, madam.
Posted in the chat box in R. How about this?
In R, we can't say anything. Analytic function defined only in the complex plane. Okay, analytic function defined only in the complex plane, not for the real line. Real line just a differential function. If a differential function vanishing this somewhere, not necessarily 0. Okay, I will explain. Don't worry, madam. This is a real line. I have a f this interval a to b. I have my f vanishing this point. Smooth curve, just a smooth curve. I've written. Just it will be lying on the x-axis for up to here. But f never vanishing throughout D. Right? F vanishes only here. This is uncountable set. It's a very good, nice question. They asked someone. This is not true for in differential function in the domain of R. I can draw the function here. This would just assume that it will be very nice, smooth bending. It's a smooth function. It will be lying on A to B in the interval. After that, it will be smoothly down. A smooth function is a differentiable function. So vanishing here only. So a differentiable function does not giving all this guarantee. Okay. We can't talk about analytic function in R. Analytic function, they are defined in the complex plane. But instead of, you can ask question like this. If in R, f is a differential function, is a vanishing in the uncountable set, whether this f is identically 0 in throughout R. No, I have an example. This is not this is one example. We have a lot of example. This function has a 0. Every point here is vanishing. Every point vanishing here. But differential function does not have this property. But analytic function in C has a property. That is what we are giving more important for analyticity. Okay. differential function does not have this quality. Analytic function has this quality. Okay, that is what we are studying, this analyticity. When we go and read with applications of analyticity where we are using in the real life, then you can realize why we are studying analytic function. What is the why we are studying the complex plane? Okay, anyway, nice. Is there any question, please? If you asking many question, more and more question, I'm feeling very so happy. In this room, nobody is here. I am only here. Okay, just I put the camera, that's all. Even though nobody is camera operating. If you ask any question, then I am feeling very happy.
No doubt, sir.
Oh, no doubt. Very good, madam. Without corona, most probably we can conduct the class in the class directly. We can arrange, but due to this pandemic period, we didn't conduct this possibilities. So that is what one drawback. But anyway, so how the online is using you guys, I don't know. But my point of view, it is enough the online. Okay, we will do some other problem. The same thing, same like question. And I think to give any hint, you have to say answer. You have to say the answer. Okay. Let f be an analytic function in C. Then f is constant. If the zero set of f, the zero set of f contains the sequence A equal to an 1 by n, b an equal to minus 1 whole power n minus 1 into 1 by n. Option C, an equal to 1 by 2n, dn equal to an n if 4 does not divide n. Sorry. 1 by n, 4 divides n. It's a nice question. From that question, we can understand whether if you able to answering this question perfectly, clearly, then today class is useful for you. Otherwise, you are not understanding very clear for today class. This is just do it, work, take 1 minute, do it, very quickly do it. Please. So I will write some other problem here. Consider the polynomial. P of z equal to summation n equal to 1 to infinity an z power n, where 1 less than or equal to n less than to infinity, where a n star belongs to r removed 0. Then w equal to set of all w in the complex plane such that modulus of w less than 1. Option A, P of D, not W, this is a D, you should write D. P of D is a subset of R. D. P of D is open. closed. CFD is bounded. Please response very quickly. Come on. What is the answer
All,
for 4?
all the options are correct.
All the
That
options
was-
are correct.
This is the
Please
response
individually
for
message
GV. And
GV.
Hindu says A and C.
Yes, very good. So GV is a faculty
Yes.
or oh, Swaganti madam also they said GV is faculty or student. Please GV reply. Yes, you are correct. Nisha. From the beginning day itself, I seen that. Madam?
I'm asking GV, sir.
Okay, okay. From the first day itself, I seen the GV. GV is very sincerely attending class here. And GV is girl or boy, I don't know. They are replying very quickly. So I really appreciate. So GV is faculty or student? Still, I don't know. If you possible, just reply. Otherwise, nothing. No problem. Boy, sir. Okay, very good. Boy. Okay.
Nisha Gawali also telling that A and C are correct.
Okay, they are from Tamil Nadu or they are from other state? GV. Okay.
Tiruvannamalai, sir. GV is a boy from Tiruvannamalai.
Oh, that is my native, madam. Wow, nice. So Tiruvannamalai is my native. Okay, anyway, fine. Okay, nice. We have to solve this problem. We have time is very less. F is analytic function C. F is constant. Then zeros of the what is the question meaning? F is analytic function whose analytic function zeros. Suppose whose analytic function zeros implies that whose analytic function zeros F contains this set. Okay. What is it meaning? F is analytic in C. Then F is constant. Zero set of F contains a sequence. F has a zero. F has a zero. This is your domain D. For example, suppose this is your zero set. F contains. Wait a minute. The zero set of F contains a sequence. Okay. This is your zero set. Suppose your zero set containing 1 by n, which means what is that meaning? Means f of an equal to f of 1 by n equal to 0 for all n. That is the meaning. Okay, that is the meaning. F is analytic function whose zero set contains, which means 1 by n contains some set S. What is the set? Set of all z in D such that f of set of all f such that f of z equal to 0. That's all. This is a zero. S is a zero set. S set contains 1 by n. 1 by n. Every 1 by n. F of 1 by n equal to 0 for all n. From the identity theorem or uniqueness theorem, you can use f should be identically 0. Zero function implies constant. Therefore, this option is true. What about this? This is also same technique. This is the open unit test. This is the open unit test. When plus 1 minus 1 by 2 like that, the sequence like this. This is a sequence. Just recall that Zn f of Zn equal to 0, which implies that this sequence converges to 0. 0 point inside the disk. Therefore, f is identically 0. The same thing. Zn is like this. So then An equal to 1 by 2n. The same technique. F of just we call f of an equal to 0 for all n. From that sequence, we can conclude that f is identically 0. The zero function is constant. The same thing, but here one thing. An is a sequence. We can take a subsequence. What is our subsequence? What is our subsequence? You can take the subsequence 4 divides n. 4 divides n. 4 does not divide, just you take that sequence n. Now you are taking only for subsequence, which means A4n, like A4n. This is subsequence. Every 4n type element which divides 4. So it coming 1 by 4, 1 by n means it will be coming just 1 by n. Whatever you taking element, n na 1 by n. Now 4n na 1 by 4n. Now 1 by 4n goes to 0. F vanishing the subsequence. Actually, not necessarily to F vanishing on the sequence. It is enough. F vanishing from the sequence, so F vanishing only subsequence. It is enough to show that F vanishing throughout. Not necessarily to see F vanishing on the sequence. It is enough to see F vanishing for subsequence of that given sequence. Now this is a subsequence, F vanishing the subsequence, this subsequence converging to 0. When you're taking whole sequence, this AN does not converge. Why? When F is not a 4, 6 takes value non-zero. 10 non-zero, 11 non-zero. Does not divide 4 means that this means AN does not converge, but subsequence converging. Even though F vanishing this AN, in particular F vanishing the subsequence also. Once F vanishing in the subsequence limit inside D, then F vanishes throughout in D from the identity theorem. Okay, so this is also true, which implies that F is 0 function only. All the options are correct. Very good. All the best who are done the 4 option is correct. They understood very clearly. Anyway, we will go this problem. Consider the polynomial f of z equal. This is a polynomial. N lies between not for infinity. N could be 1 or 2, 10 or 10, 11, 13, any finite. It's a polynomial of degree n. This capital N. Okay. So every polynomial we know that is entire function. Polynomials are clearly entire function. Now, what is our D? D is our open set. D is our open set. D is an open unit disk. Okay. So F is P is the entire function. Polynomial is entire function. So entire function carries open set. What this says that P of D is subset of R. It's not possible. Not why is not possible? Polynomial is a analytic function or entire function. It carries open set to open set. D is an open set whose image should be open set. Whose image lie on this R somewhere in R. This is not an open set. Okay, why it is not an open set? If this is a real number, a real set is a subset of R. If you take this in C, this is an open set. This open set does not contain, so therefore no point interior point.
Yes, madam. In B, can you say sequence is connected?
Can you say
the sequence is connected?
Sequence is connected means that is not a meaning. What is the meaning of connected is different concept and the sequence is different. The sequence lying in the connected set. Not sequence is connected. Sequence means a distinct points now. Z1, Z2, Z3. They are distinct. That is that they are not connected. If it's a constant sequence, that is connected. Okay, connected. We need to talk first. We need a set. There is no separation. Then we say that the set is connected. But that is a different story. Just leave it that things. Now we have to try to conclude these options. D is an open set whose image is lying in the real line. So in the C complex plane, any point in the real number is not an interior point. No points are interior. Why? If a point is interior, you take there is a ball, which ball contained completely in R. But take any point in the real line, you take ball. Ball is like this shape only in the complex plane. So this ball not completely contained in R. So therefore, no points of R is the interior point. Therefore, in particular, f of these also no points are interior point. Therefore, this set is not a open. This point is not an open. Okay, we know what we know. What we know. If f is a analytic or a analytic function entire set, it carries open set to open set. This is a given open set. The image should be open. That's all. This is not open. Okay. So this is not true. F of D is open is true. F of D is closed. Once open is correct. D is false. And f of D is bounded. Yes, this is bounded. Why it is bounded? D is an open set and f is a continuous function. Every entire function is differentiable. Differential functions are continuous function. Okay. Now this is your open set, open unit disk. Now I try to conclude this is your closed set and closed and bounded set. It's a compact set. F is entire, and which implies f is analytic.
Sir, that's a doubt, sir. In the fourth question, sequence in B is convergent. Can you clarify, sir?
What, madam? Again, once more.
In fourth question, sequence in B is convergent. Can you clarify? This is the doubt.
I couldn't understand that question. The doubt.
Meera Sudarsana.
Please again type it. I will explain at the end of the session. So now I try to conclude all those options. Surely I will explain your doubt clearly and neat and type it, and madam she will explain again once more. Sorry, I couldn't understand your doubt. Okay, anyway, fine. Come to the point. F is entire. F means P of Z is entire. Okay, entire implies differentiable. Differentiable implies continuous. Okay, continuous function. Open disk is not a complex. No, madam. Okay, okay, anyway, fine. This is an open set. Now I conclude closed disk. Just I will take some closed set containing that open disk. Okay, this is a closed set, closed and bounded clearly. So closed and bounded, it will imply compact with respect to usual topology. Here we are assuming that usual topology or usual metric is a compact set. P of Z is a continuous function. Continuous image of compact set is compact. Once image is compact, compact implies bounded. Complex implies bounded. So therefore, f of D is always bounded. F of D is always bounded. So therefore, option D is correct. So the correct answer is B and D only. Okay, I think the time is run out. So madam, ask us some one question. What is that? Again, please. I don't know. I think there is no.
Do you want me to repeat the question which was asked previously?
So that somebody's participant, they asked me that questions, but I couldn't understand still. So that is what I said, that please write the question again once more, or you can ask the question again once more.
I'll ask, sir. In fourth question, in the option B, the sequence is accelerating sequence or convergent sequence, sir?
Which sequence accelerate? This one?
Meera, if you happen to be in the meeting, can you kindly text your question once again?
Oscillating question. Where? Maybe they think something, but they written something. We are understand something. It will give some misleading. Still, I couldn't understand the question.
Yes, sir. I think she's also not responding.
Maybe she will be.
No, she has sent. It is in the fourth question.
This is a fourth question. This is an oscillating sequence. Doesn't matter. Oscillating sequence, whatever it may be, doesn't matter. From the oscillating sequence, you can take a subsequence. You can take an odd subsequence. It will be always one only. It will converges to 0. Doesn't matter. Whatever the given the sequence. Now I understand what she is expecting. So this is oscillating sequence. We can apply oscillating sequence. This statement or result she is expecting. I said that whatever given the sequence, from that sequence at least you can find a subsequence. In the subsequence, f vanishing, then f throughout vanishing. That subsequence just I take it certain. That's all. Now are you okay? I think this is your point, right? Okay, very good, fine. I think, madam, the time is run out. I think I take extra time. So thank you for attending for last 1 week this program. This is a very big program. Maybe next time we can same thing. I don't know. Madam, she will explain. So what to next time. So one thing I was made a mistake in this program. So every day I will give the assignment, but so I didn't think yesterday only. I thought we will give good. Yeah, good seminar. I don't know, just I missed that things. I didn't forget. I forgot that things. That's all. Yesterday only I thought every day after the class we will give the assignment. But anyway, next time we will conduct this kind of seminar. Surely we have some other plan to do that things. Okay. Anyway, you have any feedback about this teaching, all those things, please and write and send to the madam. Then I can understand. Next time I will try to change my plan. But one more thing, again, I want to say, number of problems doesn't matter. If you do the one problem very clearly and thoroughly, it is enough to study 100 problems. Okay, per day at least 4 or 5 problems to understand very clearly, thoroughly. So 1 month you can understand each paper. Okay. Anyway, I think thank you. If you have any doubt or anything, so try to ask madam. Anyway, thank you, madam, giving these opportunities for that college, your college, SSS Jain College. Is there, madam, any question?
That was
Yes.
no questions, sir. Sir, that was a wonderful concluding session for this FDP. From today's session, we now got a wide idea to solve problems and gained a complete understanding of complex analysis. Your sessions were not only knowledge enriching and brainstorming, but were also most inviting to explore. The benefits that the participants have derived from your sessions are immense. We are very thankful to you, sir, for your exceptionally informative sessions. We are overwhelmed by your passion towards the subject. The feedback you wanted to know from us after each session shows your commitment to go an extra mile in the upcoming sessions. I thank you profusely on behalf of the management and staff of Sri Shankarlal Sundarbai SSS Jain College for Women, and also on behalf of all the participants of this FDP. Sir, we are really interested to have this kind of a session from you in future also. I thank the management, principal, vice principal for giving us the opportunity to organize this FDP. I really thank the faculty members and the participants for making this FDP a fruitful one. I'll be failing in my duty if I don't thank our technical team for all the support they have rendered during the entire session. Thank you and have a nice day. The participants are requested to fill in the feedback form using the link posted in the chat box. Thank you.
Anyway, thank you again once more. I am saying to the thank you for this participant and this college, SSS Jain College, and good luck for all the very best for going to write January 29 for that CSIR exam. Still, I don't know the date is very confirmed or not. But anyway, so good luck and do the exam. First, you try to solve the part C questions, then you will go part B, then you go and attempt. This is my point of view. That will give good score in our examination. And one more thing, suppose tomorrow the exam, today don't study anything, just be relaxed. So competitive exam, one night we can't recall anything. So every day we have to study. Okay, before the exam we're going to write tomorrow, no, we need 2 days, 1 day before. You should be very relaxed, just sleep well and take water more and more. Just randomly, just to go and write simply. If you go and do the mind, it will be work very clearly, and the problems like this kind of questions only they will be asking. Okay. Anyway, so all the very best. Go and write the exam very well. Okay. Good luck. Thank you. Thank you for this opportunities, madam. Okay. Bye, bye, madam. Can I close the session, madam?
Thank you, sir.
Thank you, sir.
Thank
Bye,
you.
sir.
Okay. Okay. Thank you, madam.